Welcome to Module 9 of the course Ultrafast Optics and Spectroscopy. In this module, we will study kinetic model of ultrafast spectroscopy. In the field of reaction kinetics, transition state theory is an important theory which explains the rates of elementary chemical reactions. According to this theory, during chemical reaction, the reactants approach a high energy activated state shown here. This state is called transition state, cross the activation barrier and then descend to products. So, reactant to product journey occurs through this transition state. Before the development of transition state theory, the Arrhenius rate equation, in which temperature dependent rate constant is expressed as K rate constant equals pre-exponential factor A multiplied by e to the power minus Ea by RT, where K is the rate constant, A is the pre-exponential factor, and Ea is the activation barrier. This activation barrier Ea. So, this Arrhenius equation was widely used to determine activation barrier to the reaction. Arrhenius equation was derived empirically from experimental observations and ignored mechanistic considerations. This is why further development was necessary at that time to understand Arrhenius parameters A and Ea at the fundamental level. Transition state theory for the first time successfully provided analytical meaning of Arrhenius parameters. The whole trip from reactants to product, which often involves almost 10 angstrom nuclear configurational change in a particular molecule, takes typically several hundred femtosecond. So, let us say it is 100 to 500 femtosecond to undergo this 10 angstrom kind of configurational change. Consequently, the intervals at which one needs to record or observe the event in which nuclear configuration evolves through the transition state are at least in the range of 10 to 50 femtoseconds. So, if I want to observe transition state, then I have to record the experimental result in this time step, 10 to 50 femtosecond time step. The objective of the present module is to present early thinking of ultrafast transition state dynamics employing a semi-classical picture of ultrafast transition state dynamics. Although the kinetic model does not include coherence, which is quantum effects. What does it mean? It means that let us say I have an excitation going on starting from V equals 0 state, vibrational state, to the upper electronics vibrationally excitation. This is called vibronic transition. So, when I use an ultrafast pulse, because of the broad bandwidth, it can simultaneously excite all these vibrational states, and superposition of all these vibrational states gives rise to the wave packet. So, this is called quantum effect or coherence effect, and in the kinetic model we will not use this coherence effect. In the kinetic model, we will illustrate other aspects of observed femtosecond transition state dynamics, including nature of population change, role of finite temporal width of the pulses, cross section, and etc. In the study of transition state dynamics, pump probe configuration can be employed. In the pump probe configuration, I can remind, we use always a beam splitter to split the beam, and then we have mirror to direct the beam, and these two beam will be collinearly propagating along this direction. So basically, if these path lengths are the same, then we get two pulses overlapped, and these two pulses, one of them is called pump and another one is called probe. So this there are many detection schemes which can be used in the pump probe configuration, such as fluorescence, absorption, multiphoton ionization, four-wave mixing, etc. However, here in this module, we will go over the detection technique related to ionization detection scheme. So we'll go over the one interesting experimental result. This result is related to an electronically excited dissociative state of acetone molecule. This acetone molecule can be excited to an dissociative state with the help of two photon excitation, and then from this excited state, acetone molecule can be further ionized with the help of single photon excitation. So this is the probe, and this combined two photon is pump, and this state is dissociative. Acetone molecule, in the experiment, gas phase acetone molecules were photoexcited to the dissociative state, more specifically a broad 4s mixed Rydberg state by two photon absorption at 307 nanometer. And the excited parent molecules were then ionized by one photon absorption at 615 nanometer. By changing the delay time between the pump and probe pulses, the temporal behavior of the dissociative excited state prepared by the pump pulse was monitored using a mass spectrometer. So once we have created this positive ion, that positive ion can be accelerated in a mass spectrometer and can be detected with MCP detector. So this is mass detection scheme which has been used. The pump probe transient as a function of delay time is given in this figure. This delay corresponds to the delay between pump and probe pulses. If you look at this figure, there are a number of questions which are obvious to us. If we look at the negative delay portion, we see ion signal. We can ask why we should see ion signal in the negative delay. Negative delay corresponds to the fact that probe pulse coming earlier than pump pulse, which means probe cannot excite the molecule to the excited state. It is only pump which can excite the molecule to the excited state. In spite of this fact, we are seeing some signal, ion signal, in the negative delay. On the other hand, if you look at the maximum of the signal, it doesn't appear at the 0 time delay. Question is why? And from this transient profile, we'll be able to extract dissociation constant K. Question is how? So with these questions, we'll go over the ionization detection scheme. Before we begin thinking about electronic transition by a short optical pulse, which contains different frequency components, let us first understand the electronic transition by monochromatic photons. As we know that if I have a pulse, this is in time domain, then in the frequency domain I will have a distribution of frequencies, which means I have delta omega, and this is unavoidable for a pulse. However, here we will begin with monochromatic excitation, which means I have only single photon to excite or ionize, and then we will extend this idea to the ultra fast spectroscopy. Consider a molecule A in an electronically ground state. This is excited by monochromatic pump photon H nu pump from its ground state to an electronically excited state A star. So, A star is an electronically excited species. A star dissociates to photoproduct P, and we can say that first order kinetics is followed for an example. So, if A star is dissociated to P, then we can write down dA star dt equals minus of A star concentration. That rate equation we can write down. We'll go over this kind of rate equations soon. To get a simplified picture, let us not invoke other photophysical processes. When we excite the molecule to the excited state, we can have fluorescence, emission, or many other processes, internal conversion or intersystem crossing. We will just forget those processes. We will just think of only dissociation process from the excited state. After a time delay tau, so I have a pump pulse, and then I have a probe monochromatic, I have pump, I have probe, and they are separated by a delay delta tau. This is a very hypothetical experimental condition. Here we have assumed that we have monochromatic pulse. It's just an assumption. In reality, no pulse can be monochromatic, but it is an assumption, and we are saying that these two monochromatic pulses are separated by delta t time. So, after a time delay, another monochromatic probe photon ionizes A star. So, this A star is ionized to A plus. A time of flight mass spectrometer then detects the ion A plus. The moment I create, so I have two beams, pump and probe, and I am creating A going to A star, then going to A plus. The moment I create this A plus, this will be detected in time of flight mass spectrometer. This is one kind of mass spectrometer. Mass spectrometer is sensitive to only A plus ions, and it is quite clear that A plus can be generated by the joint action of the pump and probe photons, which means that the ion signal would be proportional to the A plus concentration or number of A plus we are creating. If the excitation followed by ionization scheme is repeated for different time delays, a time varying ion signal can be recorded as a function of the time delay, and a so-called transient profile is obtained. The photodissociation rate constant this k can be estimated directly from the transient profile. In order to estimate k, however, we need to develop response function, an important term. Response function. So we have to develop the response function for excitation followed by ionization scheme. Response function is what we measure in the experiment and which contains all the dynamical information. Response function can be derived solving kinetic rate equation of the electronic transitions involved. So let's look at how to represent electronic excitation transition rate. To understand the kinetic rate equation of electronic transition, let us first consider that the initial population of A in the ground electronic state is Na. Na is the population in the ground state. This is the ground state from where we are exciting the molecules. Now, if we have any number of molecules, it is not possible that all the molecules are excited by the pump beam to A star, because there is a probability of transition. This pump induced excitation cannot be 100%. Instead, a fraction of ground state molecule A is excited by the pump beam. The rate of this excitation is determined by two factors, therefore. The cross section of absorption of a pump photon by a molecule. So this probability of transition is given by sigma A star, which features the probability of absorption of a photon by one molecule A in the interaction regime and total number of photons impinging per unit cross section area per unit time. So these are the two factors which will control how much population I will have in the excited state, probability and how many photons I have and how many molecules I have. To estimate the rate of transition, we shall begin the discussion with Einstein's quantum theory of radiation. Based on this theory, number of photons can be calculated as follows. Number of photons is nothing but the total energy content divided by energy content of each photon. So number of photons per unit area is again total amount of energy divided by each photon energy divided by cross sectional area pi r square. Now by definition, intensity is nothing but energy per time per cross sectional area. If we try to find out number of photons per unit area per unit time, then that is given by intensity divided by h nu. So the fraction of molecules which are excited per unit time and per unit area, that will be given by number of photons coming per unit area per unit time multiplied by the cross section. So rate of transition per cross sectional unit area will be given by this fraction multiplied by total number. So what we see is that the rate of transition, this rate depends on three components: probability of transition, number of photons, number of molecules. So now question is, this RAA star, what does it mean by this RAA star? This RAA star rate of transition is rate of transition per cross-sectional unit area due to pump radiation. For an example, if RAA star divided by NA for a particular process is 0.1, is 0.01, then it suggests that 10 in 1000 molecules is excited to the excited state per unit cross-sectional area of the interaction regime. Similar rate equation can be derived for the subsequent ionization process. Here, ionization process. So, this rate is excitation and this rate is ionization. And again, it depends on probability of the ionization from the excited state, number of photons in the probe, because probe is inducing the ionization, and number of molecules which are in the excited state. So, there are three components which will control this. Now, here we note that Na star, that is the population in the excited state, depends on the time delay between pump and probe beams. Na does not depend on the delay. Na is number of molecules I have in the ground state, but number of molecules excited in the excited state depends on the time delay between pump and probe beams, because if the probe beam comes too late, by when all the A star molecules has dissociated, all the A star molecules have dissociated to P, probe beam will not see any A star population, and as a result I will not be able to prepare any ion. Consequently, time of flight mass spectrometer will not detect any signal. So, in order to observe a signal, pump and probe, the delay between pump and probe cannot be too long. How long it could be? It depends on the how quickly they are dissociating. These excited state species are dissociating. So, in this derivation, the pump and probe beams were treated as monochromatic beams. As I have told you, they are like a pulse. So, it is a hypothetical or imaginary experimental scheme where their pulses looks like this and their frequencies are also like this, which is impossible to get. Shorter the pulse is, broader the spectrum would be. So, in time domain the difference is delta t, delta tau, and in frequency it is having h nu, this is pump and this is probe. So, that is an imaginary excitation process we have thought of. However, ultrafast pulses are not monochromatic light source. In fact, no optical pulse is monochromatic. They have a finite bandwidth. This feature of short pulse exhibits significant influence on the detected signal. If we want to extend these equations to the ultrafast spectroscopy, we need to understand how to define h nu for an optical pulse. In addition, pulse intensity is time dependent. So, whatever I we are writing, this would be time dependent for a pulse, and question is how do I define this h nu for a pulse, because there will be many frequency components in a pulse. To derive, to get kinetic model of femtosecond dynamics, we shall consider only center frequency component of the pulse, in spite of the fact that optical pulse contains a number of frequency components. Furthermore, finite temporal width of the pulse will be explicitly taken into account. So, in order to extend these equations to the ultrafast spectroscopy, what we'll do to develop this kinetic model, we'll do one thing. This is the pulse temporal profile. This is I profile as a function of time. Let's say this is a Gaussian pulse, so it will be centered at t equals 0. And corresponding spectrum is like this, it is centered at omega naught. This omega naught is center frequency. So, we will consider full temporal profile of the pulse, but we will consider only the center frequency of the pulse. So, this is our strategy to develop the kinetic model. Thus, the transition rate equations in the context of ultrafast spectroscopy may approximately written as Rij. Let's say I am undergoing transition from ith state to jth state, and I have population Ni, so rate will depend on Ni. I have excitation pulse, many frequency components are present. However, I will consider only center frequency component, which is h nu naught Ij. That is why it is number of photons, and explicitly I am treating t as a function of time. Explicitly I am treating intensity as a function of time, and I have the probability of that transition. Now, this Ij, this intensity profile, how can I represent this intensity profile in terms of a normalized function intensity profile? I can do it with the help of this equation. So, if I is the intensity profile, normalized intensity profile, then from minus infinity to plus infinity, this intensity profile, if I integrate, it will always give me 1. So, finally, if I integrate minus infinity to plus infinity any intensity profile, we know that this equation is nothing but related to the energy content, which is E divided by pi r square, because this integration minus infinity to plus infinity I bar t dt, this is going to be 1. So, effectively we are getting an energy content in the pulse. So, I will express intensity profile in terms of its normalized intensity profile. So, finally, what I get rate of transition, probability, it depends on probability, number of molecules, and then rest is just number of photons, is related to number of photons, but it is expressed in terms of normalized intensity profile. The excitation by the palm pulse alone results in buildup of A star population, and if for now no photodissociation of A star is invoked, then the rate law for A to A star's transition can be written as follows. So, what I have is that I am considering only photo excitation from A to A star by pump pulse. So, I am just looking at the effect of pump under the scheme we have already discussed, and we are saying that this A star is not dissociating at all. I am just preparing it. So, My ultimate target in this derivation, current derivation, is that I want to know how the build-up signal look like. For that, I have to prepare the kinetic equation, which is nothing but rate of build-up of A star, which is rate of transition, which is given by this equation, where I am considering normalized Gaussian intensity profile, which is given by this. This is the Gaussian normalized Gaussian intensity profile. So I plug that in here, I get this equation, and then all we need to do is that integrate this from minus infinity to any time t1. What does it mean? I have a pulse here, and it has intensity profile like this. This is minus infinity, and I want to know at any time from minus infinity to this time what would be my build-up signal NA. So this is my NA signal. How much would be NA as a function of time? Very soon we'll see that it follows like this. So what I'll get is that each point is the integration from minus infinity to that particular t1. T1 is a parameter here. So this is t. This is shown here again. So each point here representing an integration from minus infinity to t1. Again, this is minus infinity to t1. This is minus infinity to t1. So t1 is becoming a variable here. This t1 will be converted to x1 very soon. That's why it is shown in x1. But the normalized intensity profile is shown in the time domain, and the variable is here t. So effectively, I am interested in this integration minus infinity to t1 e to the power minus 4 ln 2 t square divided by delta t square dt. This integral is nothing but the area under the curve. That's why each point corresponds to the area under the curve from minus infinity to a particular t1 to get the build-up signal. So this is this build-up signal is related to NA star. This is a direct connection. There is a direct connection between the error function and normalized Gaussian function, because the nature of this function is called error function, and there is a direct connection between error function and the normalized Gaussian function, and we get that connection if we take the integration of the normalized Gaussian function from minus t1 to plus t1. So I am just considering, let's say I have a Gaussian function, normalized Gaussian function, and I have to take an integration from minus t1 to plus t1, and this is t equals 0. So if we take that integration, then how can I get this integration done? First I'll assume this, very simple, then I plug that in and we get the limit x1 plus minus x1. So finally this integration, after making this after inserting this, we convert this integral to this, and finally we get an integral like this. Because it's a Gaussian function e to the power minus x square, that's why we can write down this integral as minus x1 to plus x1 e to the power minus x square dx. This can be written as twice of 0 to x1 because it's a symmetric function, and that's why this 2 factor is coming in. And finally, I get this integral. This integral is called error function, and error function is a function of x1, which is this limit. So this figure shows the Gaussian function which is centered at x1, x equals 0. This figure shows that this Gaussian function is centered at t equals 0. The error function, which is obtained by integrating the normalized Gaussian distribution in the limit 0 to x1, is then plotted here, and we know x1 is related to t. x1 is nothing but t1 square root of 4 ln 2 by pi delta t square. So the integral of normalized Gaussian function can be written as, this is what we want to know, because our dA star dNA star dt, that rate equation had this this NA star population build up signal NA star T1 has an integral which was minus infinity to T1 e to the power minus 4 ln 2 t square divided by delta t square dt. So this integral was present in the build up signal. That's why we need to find out this integral. And when we are trying to find out this integral, we have to, because this is a normalized Gaussian function, then minus infinity to t1, this integral can be written as minus infinity to 0 plus 0 to t1, and because it's normalized, this would be half, and that's why this factor, and then plus this integral, which gives, if we again substitute, and finally we get this function. So finally we get the build up signal, which is nothing but this, which will depend on this integral, and after doing this integration we get, this is the build up signal, which depends on the error function. Now if we vary T1 parametrically, the normalized buildup of a star state population for a Gaussian pulse can be plotted here. So this is the Gaussian pulse, and this is the build-up signal we have plotted here, which follows a error function, which follows an error function behavior. It is interesting to consider the build-up of A star due to another shape of the pump pulse. If we consider now delta function, then we will get NA star is nothing but sigma A S star Na E pump divided by H nu naught A S star pi r square. So, the moment I come to this 0 point, I get the maximum signal, but in case of Gaussian pulse, maximum signal does not appear at 0 time, it appears at some positive time due to involvement of this error function. We will stop here, we will meet again to continue this module.